Our project is on circuits. An electric circuit is a path through which charges can be conducted. So here we built a simple series circuit. A series circuit is a single conducting path without junctions. So when I connect these wires together, the light bulb should light up. The power source for this are these three batteries that are connected here. The charge inside the battery goes through this wire into the light bulb, down through this other wire into the other light bulbs, until it gets to the other end of the battery. Okay, so how we connected the wires to the light bulb was we took the wire and we put it on the metal base right here, and we covered it with tape to stay. Now what happens is when the charge goes through this wire, it gets conducted into the metal base, up through the filament into the light bulb, down the other side, and out this base here, into the next wire that we connected, which runs to the next bulb. Inside the filament, the electric charge is going to collide with the atoms of the filament. All these collisions are going to change the electrical energy into thermal and light energy, so you can both see and feel the energy. Alright, in a series circuit, the potential difference across the entire circuit should equal the potential difference across each light bulb. So, using this meter here, we're going to be looking at these numbers down here, the 0, 2, 4, 6, 8, 10. When I connect it to the two ends of the circuit, the meter reads 3 volts. Now, so when I measure on each side of these light bulbs, the sum of their voltages should equal 3. When I connect it here, it reads 1. When I connect it over here, it also reads 1. And then when I connect it here, again it reads 1. So that added up equals the 3 from the two ends of the circuit.
Okay, the resistance between each light bulb should be equal. And as you can see on the multimeter, they are. And when you add resistors, in this case the light bulbs to the circuit, there's less current going through each resistor, which makes them dimmer. And if you measure the resistance between different light bulbs, they add up. Okay, so we've broken one of the light bulbs. So since this is a series circuit, it creates a gap in the electricity, so it can't go through the filament and go to the other light bulbs, which makes all the light bulbs. So here we have another series circuit with only two light bulbs instead of 3. There's less resistance, which means more current going through each light bulb, which makes them brighter, as you can see. We're going to measure volts first. If you measure each one, they should be equal. And they're going to be 1.5, as you can see on the multimeter. And then if you measure them together, they should be 3 because this should add up. Now we're going to measure resistance, and they should be equal. And they are. And if you measure them together, they should add up.
Okay, so here we have a parallel circuit. A parallel circuit is when you have more than one route for the electricity to travel. Here we have the electricity will travel from the positive end of the terminal through the wire, and then it'll split up here. Some will go through this light bulb, some will go through this light bulb. It'll connect again and complete the circuit. The benefit to the parallel circuit is the alternate route for the electricity to travel. If one bulb is removed or goes out, the other light bulb will remain lit because the electricity will have another route to travel. Unlike a series circuit, the potential difference or voltage will remain the same across each bulb. Now this is because each side of the bulb is connected to common points. these 2 points being the 2 terminals of the battery. To prove this, we're going to measure it. As you can see, it reads 2. And when we measure the other one, it also reads 2. Okay, so if we want to find the current going through this parallel circuit, it is slightly more difficult than finding the current going through a series circuit. Now remember here, the electricity goes through, the current will go through this wire and it'll get divided. Some will go through this light bulb and some will go through this light bulb. That means each light bulb has its own current, and we must add the two to get the total current. Now, if we measure the resistance, we'll notice that it's not always constant. If we measure on either side of the bulb, it's going to read about 4. If we measure on the other side of the second bulb, again, it reads about 4. Now, if we measure at the ends of the circuit, we notice it reads 2. So, why is there a drop in the resistance? Well, this is because when you measure on either side of the bulb, you're measuring the resistance of that bulb. When you measure the resistance at the 2 ends of the circuit, you are measuring what is called the equivalent resistance. The equivalent resistance in a series circuit is simple. It's just going to be the sum of the resistances of each light bulb. But in a parallel circuit like this, you're going to add up the reciprocal sums of the resistances. This can be explained with a few simple equations. So first, take a quick look at the schematic diagram here of what we have as a circuit. Here's the battery source, some wires connecting down into the 2 bulbs. We measured voltage as 2 volts, the resistance across the first light bulb as 4 ohms, the second light bulb as 4 ohms, and when we measured the current, we got 1 amp. So we're going to use the equation voltage equals current times the equivalent resistance. As I said with the parallel circuit, the current is going to be divided up in between both bulbs, so we have to add up the current of light bulb 1 plus the current of light bulb 2. If we take this equation up here and rearrange it for current, we'll get I equals V divided by R equivalent. If we substitute this equation in for over here, we'll get the total current equals the voltage of the first light bulb divided by the resistance of the first light bulb plus the voltage of the second light bulb divided by the resistance of the second light bulb. So if we want to figure out why the equivalent resistance equals the reciprocal sum of all the resistances, we're going to look at this side of the equation. Because we know that all the voltages in the entire circuit is going to be equal, we can divide both sides by V, and we'll get 1 over R1 plus 1 over R2. Now we have R1 and R2 right here, 4 ohms each. So we'll do 1 over 4 ohms plus 1 over 4 ohms. Now this is essentially saying 0.25 over 1 ohm plus 0.25 over 1 ohm. And that's going to equal 0.5 divided by 1 ohm. Now we need to take the reciprocal of this because we want ohms in the numerator and not the denominator, which is why this is called the reciprocal sum. So if we do 1 ohm divided by 0.5, we'll have 2 ohms as our reciprocal sum of all the resistances. Now, if you want to make sure this number is correct, which it is because we measured it, but if you want to plug into the equation to validate everything, we'll do voltage equals 1 amp as we measured times the 2 ohms of the equivalent resistance, and that's going to get us 2 volts, which is what we had. To see the benefit of the parallel circuit, we replace the good light bulb with a broken one, and we notice that the other 2 lights are still on because there's an alternate route for the charge to go. This is our complex circuit. It is a combination of both the series and the parallel circuit. we have a series here and a parallel here. As you can see, these two bulbs are much dimmer than the one in the series, and we'll turn off the light so you can get a better look. They are on, just barely though. So now we're going to explain why those are so much dimmer than the one in the series.
Now we will mathematically find out why those two bulbs in the parallel are dimmer than the one in the series circuit. As you can see here, we have the batteries. This is representing the batteries with 5 volts. And each one of these little circles is the light bulbs, each with 4 ohms of resistance. And this equation up in the corner is voltage equals current times resistance. Okay, in this example, we'll say the current is flowing this way with 5 volts. To find the voltage in the parallel circuit, we need to find the voltage drop in this bulb. And to find that, we use this equation where I is the total current in the circuit and R is the resistance of the bulb. And V is the voltage going through the bulbs. Okay, we need to find I, or the current in this equation. To find I, we switch the equation to equal I equals voltage over equivalent resistance. And to find equivalent resistance of the entire circuit, we do the equivalent resistance of the series and the equivalent plus the equivalent resistance of the parallel. Alright, to find the equivalent resistance of the parallel, we need to find the reciprocal sum of the resistances, which is 1 over 4 ohms for both of them. So we add those two together, we get 2 over 4 ohms, and then we find the reciprocal of that, which is 4 ohms over 2, which gives us the total of 2 ohms. And we plug that into where it says equivalent resistance of the parallel plus equivalent resistance of the series, which is 4 ohms as we know before, and we get a total of 6 ohms. Okay, now that we have this total equivalent resistance of the system, we plug that into equivalent resistance under voltage, and the voltage we have is 5, so we just do 5 voltage over 6 ohms to give us a total current of 0.833 amps. So now to find the voltage drop in the first light bulb, we take the resistance of the first light bulb, which is 4 ohms, plug it in here, and we take the current we found, 0.833, and multiply those two together to get 3.33, which is the total voltage drop in that light bulb. And we take the current voltage, which is 5, then subtract the 3.33 voltage to get a total of 1.66 total voltage remaining. The remaining 1.66 voltage will be transferred into the parallel circuit and distributed evenly among the two remaining light bulbs, giving each of them 0.83 voltage. And the reason those two are so dim is because that's such a lower voltage than the first one of 5 volts, which explains why they're so dim.
Now I want to show you how in any circuit, the current or flow of electricity is direction independent. Right now we have the positive end right over here, so you would think that the current is going in this direction. So you would think that if we flip this around, it might change the brightness of these bulbs, like make these brighter and make that one dimmer. So we'll just flip it around and show you what that looks like. So as you can see, we've switched this around, so the positive end is over here. So now you'd think the flow of electricity would be this direction, but as you can see, the brightness has not changed, meaning that the flow of electricity is path independent, or direction independent, sorry, and meaning that the electricity is kind of everywhere at the same time.
Okay, so the next item we're going to show you is your common household circuit breaker. More than likely you have one of these in your house.
No, Mike, I'm pretty sure every house has this.
Alright, it's very rare to find a house without a circuit breaker.
No, like, literally every house has this.
Okay, every house has a circuit breaker. Sorry, Jeff. Okay, and the circuit breaker is wired in both a series and a parallel circuit. It is a series circuit because if you shut the main master switch off, then all the house will go dark. But it is a parallel circuit because if you turn off just one of these ones, say the washing machine one, then just the washing machine room will go dark. Or if like you turn off the cellar sheet switch one, just the cellar goes dark. And then it's just, yeah. Alright, in this experiment, what we were doing is we've taken the cover off of a typical disposable camera to show you how a capacitor works. First, the parts that we point out is this is the battery, that is the power source of the camera. This is the capacitor right here, this little green tube. And these two poles right here are what the capacitor charges. And those will release the charge when they're charged. But they're not charged right now. And this is the circuit board that will lead into the capacitor to charge it. And to charge the capacitor, what you do is you hold down this lever. And you should be able to hear that. And then now the capacitor is charged. And what happens is, when these two poles are touched to another object, they will discharge their current charge into that object. So say this piece of metal on this paint chipper, it will get all the charge from those two poles and create sparks in the form of thermal energy, and you'll be able to hear a sound.
Okay, so here's what we're going to do.
Stop! Before you can do that, you need protective handwear.
Thanks. Hey, wait! Who are you?
I'm Mr. Salmon.